the conference today. We're going to continue now with the second part of the three-part series by Wyacheslav Futorny, who's going to talk about infinitesimal algebras. So thank you very much for coming and to Wyacheslav for being here.
Thank you very much, Mathew. So I don't think I was talking too much yesterday at the beginning, and I don't think I thanked enough to the organizers. So I would like to do it to all of you for the great organization, and to Adolfo for inviting me. And we've known each other with Adolfo for quite some time by correspondence, but then finally we met, and we keep in touch. Yeah, thank you very much.
Thank you.
Yeah, so this is the last picture I wanted to show. I thought I should keep up the tradition that I started, but I don't have enough for tomorrow, so this is the last one. And this was taken 1 month ago at the meeting in Amazon area. Right, so you can... No, piranha, it doesn't exist of this size. No, this is called tambaki. Well, it can be like that, but at most. No, this is tambaki. I did not catch it, but I ate it. Yeah. Mathew, please. Okay, so yesterday we discussed Lie algebras of vector fields on, first of all, on the torus. And today we continue with other infinite dimensional Lie algebras, and also I promise to come back to discuss Lie algebras of vector fields on arbitrary affine varieties, so we'll do that too. Well, as we already saw in the Katz theorem, the classification theorem of Z-graded Lie algebras, so I should say Katz-Mathew theorem, affine Katz-Moody algebras appeared, while they were not called this way in those days. And so they attributed to both Victor Katz and Robert Moody, who independently introduced this class of algebras from different perspectives. So Victor Katz, as we saw, was working with the classification of Z-graded simple Lie algebras, and well, Robert Moody was generalizing the idea of the root systems for finite root systems, and he came up with this idea. So as we know, any simple finite dimensional Lie algebra, so I'm working over complex numbers, as we agreed, can be parameterized by a Dynkin diagram, or as sometimes Canadians object, they say they should be called Coxeter-Dynkin diagram, but Dynkin diagrams, or equivalently by a Cartan matrix. Cartan matrix is a matrix with entries AI. If they are off the diagonal, they all equal 2 on the diagonal. The zeros are symmetric, so if appears 0 on the ij's place, there should be a 0 on ji's place. And the matrix is symmetrizable, which means there exists a non-degenerate diagonal matrix D such that dA becomes symmetric. And to get a finite dimensional algebra, so the requirement is that the symmetrized matrix is positive definite. So we can picture the Sylvester criteria that the determinant on all principal minors are positive. So each such matrix parameterizes, if it's a decomposable matrix, it parameterizes a simple isomorphism class of simple finite dimensional Lie algebras. And they can be defined by generators and cell relations. Okay, now we can generalize this approach by dropping some condition. So let's forget that the last condition for the matrix to be a positive definite. So if we erase it and keep and erase symmetrizability, but keep all other conditions on the entries of the matrix, we get what is called a generalized Cartan matrix. And if we use the same construction with generators and relations, what comes out is the Kac-Moody algebra. And Kac-Moody algebras are divided in three groups. The first group is exactly finite dimensional ones. The second one is affine Kac-Moody algebras. They correspond to the case when, instead of positive definite, we impose a condition that the matrix is positive semi-definite, and which amounts, together with all other conditions, so it implies that the determinant must be zero, but all other principal minors are still positive. And that corresponds to affine Kac-Moody algebra. For example, if you take matrix, 2 by 2 matrix with entries 2 minus 2 minus 2, 2. That's a typical matrix for this case. Okay, how do we construct them explicitly? So we already had this construction yesterday. So we can start with a simple finite dimensional Lie algebra G, right? And tensor with Laurent polynomials in one variable. So then naturally, as we saw yesterday, we can have a Lie bracket on this tensor product, and we get an algebra, a Lie algebra, which is sometimes called loop algebra. So this way we don't get all affine Kac-Moody algebras, but roughly half of them, and they're called non-twisted or untwisted ones. They usually, instead of just working with the loop algebra, we consider the universal central extension, which is again in this case, as we saw in the case of the first Witt algebra, when we get Virasoro algebra, this universal central extension is one-dimensional. And we throw in a derivation d. So d is a degree derivation that behaves this way, and the Lie bracket now changes. And so here's an old part, and now due to the cocycle, we get this multiple of the central element C. So C is now a one-dimensional center. So this algebra, so we can picture it, these are non-twisted affine Kac-Moody algebras. So what about the others? Well, suppose, so it should be automorphism here, a missing symbol. So sigma is an automorphism of G, of the degree of order L. And let's fix a complex number, which is a Lth root of unity. So this is my loop algebra as before. So let's denote it by LG. And now we associate with the fixed sigma, the sigma tilde, an automorphism of LG. And we look at the fixed points of this automorphism. So I denote it here. So this, we get a Lie subalgebra of LG, and this is the class of twisted affine Lie algebras. Sigma can be chosen just in symmetry of the Dynkin diagram, the automorphism of the Dynkin diagram. And this way we parameterize the isomorphism classes of twisted affine Lie algebras. So if you think in terms of Dynkin diagrams, so for the first class of untwisted affine Kac-Moody algebras, to get a corresponding diagram, which is called extended Dynkin diagram, from the classical Dynkin diagram, we just add one vertex and some issues. And similarly, there are extended Dynkin diagrams to this case. I did not write explicitly. I mean, this is well known. If you are interested and you've never seen it, it's easy to find. But if you think of type A, so let's take a simple finite dimensional algebra SLN. So the Dynkin diagram, you have a line with endpoints. So if you do affinization, we do extended diagram. So untwisted one way at one point, and we join to form a triangle. This will be extended linking diagram of type A. Okay, there's always important question whether we can realize our given Lie algebra in terms of differential operators. So there are classical realization which are called free field realizations for affine Lie algebras. So let's consider the case of SL2. So the affine SL2 has a basis En, E sub n, so that's so we choose a basis, standard basis for SL2, E, F, and H. And so this is the basis for SL2 hat. So it's E tensor Tn, so this n becomes an index here, same for H, same for n. And of course we have, if it's extended by center and derivation, there is a c, little c, and little d. So this is our basis. Well, there is a geometric way to construct a realization in differential operators for finite dimensional Lie algebras. And if one tries to mimic it in the infinite dimensional setting, it uses what is called natural Borel subalgebra, which in this case, so if we have some Lie algebra and we have a decomposition, let's suppose it contains Cartan subalgebra, so this is Cartan. And we have a certain triangle decomposition that this part, it was usually called Borel subalgebra. There are different ways, I will talk about it below. There are different ways to construct triangle decomposition in the affine setting. For example, one can take in n plus all elements En. Here I put all Fn. And then there is still Hns. So here I put Hn for positive ones, and here I put Hn for negative ones. And Cartan is Cartan, so there is H0, C, and D. This will be a triangle decomposition, and this part is usually called natural Borel subalgebra. And there is a difference between natural Borel subalgebra and standard ones. The standard ones, as we expect, is when we divide into positive and negative roots. So here are the root spaces that correspond to positive roots, and here's the root spaces that correspond to negative roots. And this is different, right? So here we have a mixture of positive and negative. So consideration of this Borel subalgebra and sort of generalizing the finite dimensional approach leads to the following formulas. So if we represent ENs by partial derivatives, so we're working with polynomial ring in infinitely many variables, xm's, and so suppose that En acts as a partial derivative, and Hn acts as infinite sum, Fn acts as disinfinite sum. So one can check that these operators satisfy the relations of the Lie algebra. So we have a representation. The problem is that this is not a well-defined action, right? Because if you apply, because of the product of these x's here, so if you apply this sum to a polynomial, you will not get a finite sum as a result. So then we need to talk about completion of the polynomial ring, and etc. But it's not a well-defined action on polynomial ring. One can correct it. And the trick is, first trick is to apply two anti-involutions. First anti-involution is when we replace ENF for all n. And the second involution is we interchange x's and deltas. And then the formulas become like that. So now Fn, x is a multiplication by xn, Hn, x, so forget about this lambda for a second, as this sum, and En, x as this sum. So these are corrected parts. And now they are well defined because we have two derivatives here on the right, so it is a well defined action on polynomials. So then this was constructed, this representation was constructed by Jakobsen and Katz, and was later was also considered by Bernard and Felder. And here we can even throw in these lambdas. And we get a nice representation of our Lie algebra SL2 on a Fock, what is called Fock space, which is a polynomial ring. So if you think what kind of representation we get, so to figure this, you just take one from the polynomial ring and apply this operator. So we see that three f's are acting freely, right? They're just multiplying by x's. But is will kill it. All is. So which means that this n plus acts trivially. So this will be like a highest weight module only with respect to a non-standard Borel subalgebra, with respect to a natural Borel subalgebra. And this example already indicates that the situation in the affine setting is quite different, because in the finite dimensional case we don't have analogs of this natural Borel subalgebra. In the finite dimensional case, all Borel subalgebras are conjugated to the one that corresponds to positive roots plus diagonal matrix. So there are no secrets in the finite dimensional setting. In the affine, so as we see here, this one cannot be conjugated to positive roots. So it's quite complicated, quite different even for SL2 hat, right? For affine SL2. In fact, for affine SL2, there is no others. So there are just two conjugacy classes of Borel subalgebras. One is the usual one that corresponds to the positive roots, and the other one is a natural Borel subalgebra. But if we go to higher ranks, then other types of Borel subalgebras appear, which is sort of mixture of two classes, two types, the standard one and the natural one. Okay, so we saw how to, from formulas, which are easy to write and which are not well defined on polynomials, applying those anti-involutions, we were able to correct them and get a nice representation. There is a different trick which uses so-called normal ordering. So consider this AZ minus and AZ plus. So that together they form a field, what is called a field AZ, which is a series in the variable Z. And if we have a product of two fields like that, then the normal ordering defined this way. So we just spread A minus and A plus part, putting A plus on the right. So the idea is that if we have a complicated series, we want to move the annihilating operators to the right. The same idea as before, right? We want to have derivatives on the right-hand side in order to act nicely.
So is this the same as the Wick ordering in physics? Is this the same as like the Wick ordering in physics with the?
Yes.
They see the notation with the colons.
Yes. Okay, so now let's introduce the sort of a while algebra. So an, depending on the index, will be either multiplication by x or partial derivative, and same for an star. This way, then they satisfy this relation, right? So that they do behave like the while algebra, sort of analog of the while algebra of infinite rank. And here's the formulas. Again, another representation of SL2 hat, which is due to Wakimoto. So the central element acts as a scalar K. E, so EZ now is a field that corresponds to En elements. So Ez is a sum, En, Z minus N minus 1. And similarly for F and H. And here we are using normal ordering. And this is called, so we obtain a representation of SL2 hat, which is called the second free field realization. Again, these formulas define the action of SL2 hat on the polynomial ring. And then again, we can ask the same question, what kind of representation do we get? And this is the one, it corresponds to, again, a highest weight model, but with respect to a standard Borel subalgebra. So it's sort of the opposite to the natural one. So by doing these tricks, either applying anti-involutions or introducing a normal ordering, we get two types of representations for SL2 hat. And then later, they were, the Wakimoto realization was generalized by Fagin and Frankel for any affine Lie algebra. And then, well, some years ago, with Ben Cox, we looked at different types, because as I mentioned, so here we get just two cases, one for natural and one for standard. But there are other Borel subalgebras in the affine setting, and then we try to find the realization for these other Borel subalgebras, and in the A type, we wrote explicitly free field realization in this case. Only for A type because it's getting quite technical, but it is possible to do for arbitrary. They were never written, I believe they were never written even the Wakimoto realization for types different from type A, because they're getting complicated. But it is possible, if you give any particular affine Lie algebra, it's possible to write them. Okay, that's I want to do tomorrow. Okay, so even we discussed yesterday that a natural way to construct representations of a given Lie algebra with a triangle decomposition like this one is by inducing. Well, so this is the case of Borel subalgebra, right? But in general, more general, we can look at the case of parabolic subalgebra. So Borel corresponds to the case when in the middle we have Cartan. But assume now that I have my Lie algebra G, and here I have, I will call it P minus, P0, and P plus, which here I have some, if it would be finite dimensional, then I would say, so here P0 is my reductive Lie subalgebra. So this would be a reductive, and here is part of a nil radical P plus and P minus is the opposite one. And this would be a parabolic subalgebra. But imagine that I have this more complicated triangle decomposition, but where P0 could be larger than Cartan. It just contains the Cartan. Then we can play the same game, right? We can take a W, irreducible module for P0, and we can ask P plus act trivially, and then we consider induced module, right? From P, so this is parabolic P, from P to G, from W. which is a tensor product of the enveloping algebra on W over UP. Yeah, over the enveloping algebra over parabolic subalgebra. And this is a nice, as we discussed yesterday, it's a nice functor that allows to construct some universal modules. And if W was irreducible, let's say weight module with respect to Cartan, then this induced module will have a unique maximal submodule and produces a unique irreducible quotient. So this is a technique to construct some irreducible modules for Lie algebra G, starting from irreducible modules over some algebra. So this is quite effective in the finite dimensional setting. And essentially this way, the classification of all irreducible modules with finite dimensional weight subspaces was obtained for simple finite dimensional Lie algebras. And classification roughly is the following. So first of all, every irreducible module, so you just picture SLN for simplicity, any irreducible module over this Lie algebra, which is weight, so Cartan is diagonalizable, and the weight subspaces, the eigen subspaces for the Cartan subalgebra are finite dimensional, then any such irreducible module is either cuspidal, in a sense, well, we discussed cuspidality yesterday, but in this case, cuspidality means that all root elements act injectively on the module. So there are no kernels. And so then either it is cuspidal or it can be obtained by application of this functor to a cuspidal module over a subalgebra, over reductive subalgebra. So classification hence is reduced to the classification of cuspidal modules, and this was achieved by Olivier Mathew. Again, he classified all cuspidal modules in this case, and they only exist in types A and C. So, which is an interesting feature. You don't have for B, D, F, G, E, these modules. So for those types, they are always induced. So all irreducible modules are obtained this way from cuspidal modules for A-type subalgebras, or C-type subalgebras. Okay, so this is the finite dimensional setting. So it is well understood and was completed in the 20th century. In the affine setting, there is a similar conjecture that the classification of irreducible modules should be very similar to the case of dimensional case, namely that it should be either cuspidal or induced from a cuspidal module by application of this functor. Only the notion of cuspidality changes in the affine setting. Cuspidal is no longer means that the root elements are injective. They don't need to be injective, and in many cases they are not. But the module will have a lattice of weights, the complete, which coincides with the coset of the H star, the dual to Cartan subalgebra. So meaning as large as possible. That means cuspidality. So you don't have holes. You remember that yesterday we were playing polo game, dumping the holes. So there's no holes in this case, but operators do not need to act injectively. So this again is a strange feature in the affine setting which has no analog in the finite dimensional case. Well, this is known for small rank algebras. Well, there's no proof either, right? So it's an open conjecture. And again, this conjecture is for arbitrary weight model, no restriction on the weight spaces. If we ask the weight spaces to be finite dimensional, then this is true. So this is our result with Zilke. Okay, So now go back, let's go back to parabolic induction. How to describe parabolic algebra? So delta will be my root system of our Lie algebra, which is a fine Lie algebra, and then a subset of roots which is closed with respect to sum, meaning if I have two roots and the is if there is no intersection between P and P opposite, but their union gives everything. So we're sort of splitting the root system into two pieces, two equal pieces, or two symmetric pieces rather. So in the finite dimensional case, the situation is very clear. Every such partition P is conjugated by the while group to the positive roots. Positive roots with respect to a fixed basis of simple roots. Right? So there is just one conjugacy class. In the infinite dimensional case setting, it's not true anymore, it's not one. As we saw in the SL2 affine case, there are two types of Borel subalgebras. Each of them corresponds to different, to a partition of the root system. So there are two conjugacy classes in this case. Okay, so now if I have a partition of the root system, then I can define a Borel subalgebra, corresponding Borel subalgebra, just by taking a sum of all corresponding root subspaces of the Lie algebra and adding Cartan subalgebra. So this gives Borel. And for SL2, so for SL2, we can picture like that. So if I am in SL2 hat, so I have two simple roots. Right, the alpha comes from finite dimensional SL2, and the corresponding one is from the extension. So imagine that here's my alpha and here's my beta. So if I take all roots that belong to this part, this will be delta plus. But here I have a diagonal which corresponds to a root delta alpha minus beta. And this is so-called imaginary root. This is the imaginary root, and this is the imaginary, so imaginary delta is here, and this is the multiple line. So in the affine case, all roots are divided in two parts. Real roots, like in the finite dimensional case, plus imaginary roots, sort of isotropic roots. So the value of delta, so this is the linear functional, so the value on any element of the Cartan except D is 0, right, which does not happen in the finite dimensional case. So there is another way to split the roots into halves. So I take this part, and then I still have this line, so I need to split the line. Well, I do it this way. Then all the roots which belong to the red area, this will be another partition of the root system. And then we have two. One is the blue one and the red one. And any partition of the root system of SL2 hat is conjugated to one of these two. Okay, so if we go to a more general or higher rank algebras, then as I mentioned, there will be other types of Borel subalgebras, but there are finitely many conjugacy classes, always finitely many, and they all are parameterized by parabolic subalgebras of the corresponding finite dimensional one. Right, so if we have a finite dimensional G behind any affine Katz-Moody algebra. So if we take all parabolic subalgebras, which are non-conjugated, for this G, each of them gives rise to a class of Borel subalgebras. Well, this is very nice. So somehow we parameterize, we can do everything from the root systems, yeah, considering partitions of the root systems. But in fact, we miss some quite natural Borel subalgebras. And here's an example. So this one does not come from the partition of the root system. And so you see here I have all ENs as before, like as in natural Borel subalgebra. And you remember that HNs were only with positive n's there. But here I am choosing any partition of integers in two symmetric parts, and indices which appear in one of them, I add the corresponding h's to my subalgebra. So if J is just positive semiline, then I get natural Borel subalgebra. So if it's a negative semiline, it will be opposite natural Borel subalgebra. But if it's something mixed, then I get a different one. And there is no corresponding root partition. Well, but essentially that's all that we miss from that approach. Okay, but this was a discussion about Borel subalgebras. Now, parabolic subalgebras, as we saw, we can do parabolic induction and get also be described easily, and most of them correspond to what is called parabolic subset of the root system. So we just drop the condition that P and the opposite of P have no intersection. So if we eliminate this condition, the intersection will correspond exactly to this part, to P0 part. And then when we choose such parabolic subset, they're classified for all affine algebras. So they produce corresponding parabolic subalgebras for all affine Lie algebras, just by taking corresponding root subspaces and adding Cartan subalgebra and generating subalgebra by them. Right, so the Borel subalgebras and a more general parabolic subalgebras of affine Lie algebras are well understood. So subset, so GP, this is the corresponding parabolic subalgebra. So it's like this one. So it has a zero part, sort of a Lie subalgebra, and then it has a positive part. And the model is induced from any reducible weight model over the V part with the trivial action of the positive part. So we get this induced model. And as I mentioned, it has a unique maximal submodel, it has unique irreducible quotient. So if we do it for Borel subalgebras, we get what's called Fermat type model. So if the Borel subalgebra was standard, then it is a classical Fermat model. The one that the main object of the category O, so they are well understood and well studied. If you start with a different Borel subalgebra, you get a different Fermat model, and so we call them Fermat type models. So they live in a different category O, completely different, and they have different properties from the Fermat models. And similarly, if you start from parabolic subalgebra, we get what is called generalized Fermat model, or generalized Fermat type models. So depending if you use a standard parabolic subalgebra, I'll start at once. I forgot what I wanted to say. Okay, so the picture is that for every Borel subalgebra defines, or every conjugacy class of Borel subalgebras defines a certain type of Verma type modules, in particular classical Verma modules. And they come with the corresponding category O, and there is no intersection between them, and the properties are completely different. And parabolic subalgebras define parabolic categories O. So some generalization of the category O case. And then we can think, okay, parabolic subalgebras, so they have this P0 in the middle. But P0 can be of two types. It can be finite dimensional or it can be infinite dimensional. Right? It can be, if it's just Cartan, so that's the trivial case, so we have Borel. More generally, we can have a finite dimensional subalgebra here, then it is reductive Lie algebra. But we also can have infinite dimensional algebra inside. And then we are inducing from irreducible modules over these infinite dimensional algebras. And this again separates parabolic induction into completely different areas, and the corresponding generalized Verma modules have very different properties. So I will talk, since the case when the Levy is finite dimensional is sort of analogous to the finite dimensional setting, I will not consider that. That's a classical situation. But the interesting part, what happens if we do it, if we start with infinite dimensional Levy factor P0? Okay, so what is the simplest parabolic subalgebra that has infinite dimensional P0? That's the one where P0 is just the Heisenberg subalgebra together with a Cartan. Right, so by L, I denote the sum of all root subspaces that correspond to imaginary roots. So we saw that, so here we have a line of imaginary roots, and this is true for any affine Lie algebra. There is always a line of imaginary roots. So I denote by delta the smallest indivisible imaginary root, and all others are multiples. And so here is all imaginary root spaces, and since they're bracket, they generate the center. So the center is here. And this is Heisenberg subalgebra of our affine Lie algebra. And then the parabolic subalgebra, I call it special because it's the simplest possible case when P0 is infinite dimensional. So when this Levy is just the Heisenberg plus Cartan. And the positive part is, as before, is all ENs. Even for the case of SL2 hat. Okay, and then now if we start from any irreducible weight module over this part, so we are taking essentially irreducible module over the Heisenberg subalgebra and the infinite dimensional Heisenberg subalgebra. And we want it to be graded to respect the weight structure. Then we define, as always, the trivial action by the positive part, and when we get induced module, it has a special name, generalized loop module. Okay, so what is going on? So we can construct an irreducible module for affine algebra starting from an simple Z-graded module over the Heisenberg. What are they? The simple modules Z-graded over Heisenberg subalgebras be high-stick modules. There is a vector which is annihilated, say, by all positive deltas, when n is positive. So if you have a vector like that in our module, and we assume that central charge the action of little c, the central element, it acts by a scalar on a simple module. So assume that this is a non-zero scalar. Then the corresponding module in a Verma module is irreducible. Well, the Verma module itself for the Heisenberg subalgebra is irreducible. So this is an example. So we can do the other way around. We can consider lowest weight module, declaring that the negative deltas annihilate certain vector. So that would be a symmetric construction. But what else? Well, it turns out that if the action of the central element is non-zero, then we cannot have, there are no other simple modules of the Heisenberg subalgebra graded, and that five-dimensional components graded. So only high low weight mode in this case.
When you say Z, you mean that the
Correct,
Heisenberg part acts
respecting-
trivially and just the center acts?
Yeah, because we have a Z-graded Lie algebra, so we consider graded modules. Well, if they're infinite dimensional, classification is not known. Classification is not known. There is a way to get a huge family of irreducible modules start from the wild algebra. So if we take wild algebra, you picture there is an X application by, and there is the rate. This will infinite rank. And then suppose I look at the representations of this algebra on which the product x and delta is diagonalizable. For all, so xi times delta I, they're all operators, they commute, and they're all diagonalizable. So these operators, x times delta for all indices, they form an analog of a Barton subalgebra in the Lie algebra. And if we work in the category where these operators are diagonalizable, then classification of all simple modules in this category is known. So suppose I take a simple module over this, let's call it A infinity, the Lie algebra A infinity. Then, if you picture this lattice, so let's just look at the two-dimensional. So this is A2 weight module, two-dimensional lattice. And then I can consider diagonals. It doesn't matter which lines. So I can produce a Z-grading from this model just by squashing all weight spaces into one along the verticals or along any other line, along parallel lines. So similarly I can do for A infinity. So I have a Z infinity lattice, but I can choose certain directions and I can squish all the weight spaces along these directions and I produce a Z grading. Well, so there is a way to do it. And then every simple module, weight module, for the A infinity Lie algebra produces an irreducible module for this Heisenberg subalgebra. And then we can take this module for the Heisenberg and we can induce and we construct modules which in a sense very wild. They have infinite dimensional components even for over the Heisenberg subalgebra. But nevertheless we get a huge family of new irreducible modules over the Heisenberg, over any affine Lie algebra, because any affine Lie algebra contains Heisenberg subalgebra. So there is this technique to obtain a new families of irreducible modules. Okay, so here's just some examples for SLZ. Again, So, so I have a Fock space, so they're just polynomials in positive axis with positive indices. And there is a natural representation of the Heisenberg subalgebras here. So when Hn so as I mentioned, the highest weight model for the Heisenberg, the one that has Hns in 0 for any n. So you can picture it like that. So it will be a string. So here's my v. And here the basis will be h minus 1v. Here's h minus 2v, h minus 1 square v, and so on. And this will be like a partition function, the dimensions of the weight spaces. And then this you can identify with x1, this is x2, this is x1 square, and so on. So there is a natural action of the Heisenberg subalgebra which realizes this Verma module or Fock space representation for the Heisenberg subalgebra. And as I mentioned, if the central charge is non-zero, then this model is irreducible. And if we do this construction, so I start with this irreducible Verma module for the Heisenberg, and I do this parabolic induction, then this, the corresponding induced module will be already irreducible when the central charge is not zero. So we don't need to take maximal submodule after we induce up. So in this case, the corresponding induced module is called imaginary Verma module. It's because it sort of corresponds to natural Borel subalgebras, which is extreme case from the standard one. Well, again, this construction can be generalized if we do this splitting. Remember, as I showed, we can do partition of integers, and depending in which part of this partition the index of the imaginary root lies, then we include it into our Borel subalgebra or not. So this is, you can view it as a sort of corresponding to a function on natural numbers valued in plus or minus, and then this p plus and p minus are defined this way. So depending on the sign, we include it either in plus or in minus. And then we get this decomposition of the, we're not on the affine level, it's a Heisenberg decomposition, triangle decomposition of the Heisenberg subalgebra. So if the function phi has all pluses, for all natural numbers the sign is plus, then this will be decomposition into positive indices and negative indices. But more generally, it works for arbitrary phi, and then we can construct the corresponding induced model for the Heisenberg. So it's sort of like a highest weight module like this one, only we don't have the beginning, because the indices are mixed. In fact, we will have the whole line in general. And this line will represent the module over the Heisenberg. But nevertheless, module is still will be irreducible if the central charge is not zero. And moreover, if we look at the corresponding induced module, as we noticed, then the module will be irreducible. Now, in this case, when we are inducing from modules, this particular type of modules over the Heisenberg subalgebra, the induced module is already irreducible. Of course, we know from the Verma module theory that the Verma modules generically are irreducible. This is clear, right? If you get highest weight generic, so the module will be irreducible. But here is even stronger. So it's sufficiently to require that the central element acts non-trivially. And then the model is already reducible. It doesn't matter what the action of other Cartan elements is. Okay, but this was for just particular modules of the Heisenberg subalgebra in the function. But somehow it suggested that maybe there is some generality in this case. And here's the most general result we could get is the following. So I will look here. So suppose I have affine Kac-Moody algebra, any, and I have a parabolic subalgebra P, such that P has this decomposition, a Lévy part and the additional part. I don't want to say nilpotent because it doesn't need to be nilpotent in general, but it's a sort of a radical. Okay, so L is my P0 and N is my P plus here. And let's assume that L, which is P0, is infinite dimensional. So it must contain, in this case, a Heisenberg subalgebra, but it can be bigger. So if we think what kind of P0 we get, it is bigger than Heisenberg, and it will look like a sum of affine subalgebras. So for example, if I have a so suppose I have a affine subalgebra that corresponds to this Dynkin diagram. So I have alpha, beta, and gamma. Three simple roots. What I could have parabolic subalgebra the following. I can take this node, so this is just a simple root alpha, and I look at its affinization. So which means I'm taking SL2 that corresponds to this alpha and tensoring with Laurent mills. And then I'm adding, of course, Cartan. Now, part of the Heisenberg will be here, because here I have H tensor Tn. This is part of the Heisenberg subalgebra for the whole algebra. But it's not all, because I have other Cartan elements. This is H alpha, right? But I have H beta, for example, which also, in this algebra, tensoring with Laurent polynomials produces part of the Heisenberg. So there is, I should add the whole Heisenberg subalgebra G. So part of it here, in fact, we can make it, because of the killing form, we can make it, and even here we can make, maybe I put here something like that. We can make it a direct sum of Lie algebras, in a sense that they commute, and this is just a part of the Heisenberg subalgebra, which commutes with this SL2. And this can be done in general, so I can always choose a part of the Heisenberg which commutes with, I can always complement the Heisenberg that belongs to the affine part of the Lévy factor to make a direct sum of Lie algebras. And this is crucial. So in general, it will look like that. So a bunch of affine subalgebras, then you extend by the remaining part, if there is one, of the Heisenberg subalgebra and the remaining part of the Cartan. And you can do it orthogonally, in a sense, because of the killing form, in the sense that they commute. Okay, and now I will look, so I consider categories of weight modules. So I'm interested in weight modules for the affine Lie algebra and weight modules for the Lévy subalgebra.
All right, so and essentially that's all I'm interested in. So I'm interested in the weight modulus over Levy, and I will allow n to act trivially, and I will get a module over P, and then I will do this induction. I will apply induction functor. Now, I will only consider those modules on which the central element acts injectively. So this will be my subcategory, WL tilde. And the induction functor I will restrict to this subalgebra. Okay, and L is a sum of two commuting subalgebras. So this L0, it corresponds to this affine part, if it exists. Right? And GL corresponds to this part, again, if it exists. And then a natural way to construct irreducible modules in the category WL for P0, which is my L, is take irreducible module over this part, take an irreducible module over this Heisenberg part, and tensor them. So if we start with such a module, I call them tensor modules. It's not true, probably, that though I cannot prove, but probably it's not true that any irreducible module over this sum of affine or a bunch of affine algebras plus Heisenberg algebra should be a tensor product of two. I don't believe this is true, but we were able to prove it only in this case. Then the induced module, since the central charge is not zero, will be immediately irreducible. And so this is the way for arbitrary parabolic subalgebra with infinite dimensional Levy factor to produce families of irreducible modules for arbitrary affine Lie algebra. So somehow it was unexpected at the beginning of the whole theory, right, why it should be like that. But it turned out that the action of the central element determines, for this type of parabolic subalgebras, determines everything. Okay, now let's go back to free field realizations. So the most general one. So I have now variables x's and y's. So x's as before, but y's are responsible for the Heisenberg subalgebra. And so the corresponding differential operators, I will call this Weyl algebra AXY. And then the first free field realization of SL2 hat in this Weyl algebra is the following, right? So we can, that's the most general one. Now we allow, before the Heisenberg was acting trivially in the previous formulas, but now the y's are involved, and the Heisenberg algebra does not act trivially anymore. And then, so you can picture that on the top I have a Verma module. All these CYs, they form a Verma module. So it's a Fock space for the Heisenberg subalgebra in the first example that I showed above. And then we're inducing from the Verma module over the Heisenberg. And then X's appear, and that's explicit action. Right, so we have a nice formula, a well-defined action on this polynomial ring in infinitely many x's and y's. And y's are positive again. Because it's a Verma module, we can only move in one direction here. And here I just wanted to give you an idea how one could generalize, how could one obtain different types or new types of irreducible modules using a different technique. So there is a functor which is called a twisted localization functor. So this is the following. So suppose I fixed one of E's or one of F's. Okay, I will call it G, and I consider this multiplicative set in my enveloping algebra. And I localize the enveloping algebra set. Then we can consider the corresponding localized module. So if I start from any weight module, I can consider localization with respect to G and define this way. So if my G I started with is injective, then M will be a submodule here. And in fact, the second localization will not produce anything. So this is localization, but also we can twist it. So there is this operator theta Z defined for any complex. Well, sum is defined because of the action, locally important action of our element on the enveloping algebra. And then we can twist it. So we can first localize and then twist. And then the combination is called a twisted localization functor. So what's important is that there exists a procedure which gives a certain functor. Then you start with a weight module, say irreducible weight module, and then you apply this functor. And the point is that the result is again irreducible. And you may lose many nice properties that the original module had, but you do get an irreducible module. And we looked what happened if we apply this functor to the first free field realization of SL2 hat. Well, in fact, you can figure out the structure of the localized module. So in a recent paper, we consider this case. So we wanted the central charge to be non-zero, because in this case, the formulas that I showed you above, so this module is irreducible. So this is an irreducible module. And then what happens if we apply this twisted localization? Well, it depends on the relation between these two scalars, J and K. K is the action of the central element, and J is an action of the Cartan element of SL2. And then the relation between them determine the structure of the corresponding induced module. So essentially it will have a Verma submodule. So we start with this M lambda given by the formulas above. The action of, so the element was F. In this case is F. So it's injective. Remember, because F is multiplication by X. So it acts injectively on our module. And then the quotient is irreducible again generically, unless we are in some degenerated case. And we can even say more, right? But the point is we can control the application of this functor in this case. So this was for the first free field realization. We also look at the second one. It's getting more complicated, and the result is not as nice as in this case. But again, it's a very effective tool in the study of representations of affine Kac-Moody algebras. Even in the finite dimensional case, this is also very effective, because you always get a new irreducible modules. But this is absolutely not well studied, so it's sort of a new field here. Okay, now I finished this general overview of the situation in the representation theory of state of the art. And now let's go back to the generalized Verma modules for the Lie algebras of vector fields that we discussed yesterday. So you remember that in the classification of all simple modules for the Witt algebras, there were two types of modules, cuspidal and the highest weight types. So highest weight types, so in terms that we use today, they are generalized Verma modules. And I want to say a few words about them. So, recall that this is our derivation algebra of Laurent polynomials. So they are vector fields, algebraic vector fields on n+1 dimensional torus. And now I want to use the degree, the z grading by T0, by this element, or by D0, corresponding T0 times partial derivative. And then it gives this triangle decomposition. And remember, we discussed the zero component, which is just a derivation algebra of Laurent polynomials in n variables, and this abelian ideal. And then the corresponding tensor module, we take corresponding tensor module over that. It is parameterized by a finite dimensional GLN module, W, and the gamma, which was an n tuple of complex numbers. And beta defines or determines the action of this abelian ideal just by multiplication by beta and then shift of the indices. Right? So here we have multi-indices. Q and M are multi-indices here. So we have a nice model over D0. We remember that we have a criteria when the tensor module is irreducible, right? Unless it appears in the de Rham complex, it is irreducible. So we can start from this module. It's over here. Then declare the D plus x as 0 and induce up. And we obtain a generalized Verma module. So we would like to know what is the structure. Well, there is a very nice result due to Berman and Bilic, not particularly about this type of modules, this particular module in general, but the induced modules. Anyway, if we apply it, we can conclude that this fellow, well, MT has a unique irreducible quotient. This is clear because we're dealing with induced module from the irreducible one, but this is absolutely not clear. Why, after taking out the maximal submodule, the weight spaces become finite dimensional? If we think back to the first free field realization that I showed, so this defines a representation with mostly infinite dimensional weight spaces. So it will look like, so it's induced from this line over the Heisenberg, and all dimensions are finite, so they correspond to partial function of this P1, this is 2, and so on. So they're finite dimensional. But after we induce up, all these variable x's that appear, they produce infinite dimensional weight spaces. So the induced module has a mixture of finite and infinite dimensional weight spaces, which is quite unusual. And we saw that it can be, generically, it is irreducible when the central charge is non-zero. In the finite dimensional setting, it never happens. You combine in the irreducible module infinite dimensional spaces, weight spaces, and finite dimensional ones. So they always separated. But here, it is possible. So in this particular case, for the Lie algebra of vector fields on the torus, this is quite surprising and quite nice, right, that we get finite dimensional weight spaces. And then the initial question is, what is the character of the thing, and can we realize these irreducible modules in terms of differential operators? That was your question yesterday. Okay, so first observation is that inside of the vector fields on n-dimensional torus, which is a subalgebra in our D0 component, there is a SLN plus 1 subalgebra naturally living inside. And since we are, I mean, this is part of vector fields on n plus 1 dimensional torus, so there is affinization of this SLN plus 1, so just tensoring with Laurent polynomials living inside. So we have SLN hat inside. So then the natural question is, so I have my Lie algebra of vector fields, and I have a module, set an irreducible module, which I know nothing about it, this L, this one. So I want to understand this module. I know that it has finite dimensional weight spaces, but what is it? Well, then I can try to restrict it to SLN hat, SLN plus 1 hat. And maybe I can identify, since all our discussion above about representations of affine Cosmode algebra, so we have a lot of information already. So maybe we can identify this restriction as a certain module for LN plus 1 hat. Then, so Billig, Molev, and Zhang, so this is a Sydney result, Australian result from 2008. So they look at the case when n is 1. So n is 1, so we have vector fields over two-dimensional torus. So in this case, we just have three parameters, three complex parameters that determine this simple module. And suppose we restrict it on SL2 hat, right? So n equals 1, so we get SL2 hat living inside. And it turned out that generically it will be reducible again. So for generic values of the parameters, if I take that irreducible module over vector fields on a two-dimensional torus and I restrict to SL2 hat, it will be reducible. That's already a big thing, right? And moreover, they were able to recognize this module. And it looks, it is a generalized Verma module for SL2 hat. And for SL2 hat generalized Verma modules, as we saw, they can be generalized either from the Heisenberg or from SL2 or from Borel, or highest weight module. So this is not highest weight, it generalized indeed, induced from SL2. So the string, infinite string in both directions, so that's a weight module irreducible for SL2, which depends on two parameters. If parameter is irreducible. Okay, so and general Verma modules for SL2 had used from SL2, they are well understood. So there is a clear picture, and the characters know, and the module in the restriction is irreducible, so we know everything. So we're able. Naturally, conjectures immediately were stated that this will always happen, that restriction on SLN plus 1 hat will be reducible, and it will look like a generalized Verma module. And that's the end of the story. Well, it turned out to be wrong. So this n equals 2 is a special case, and it doesn't work in general. So when we tried to prove the conjecture, we could not. And then we figured that the main reason was that the module that we get is not a generalized Verma module when n is greater than 1. So it will be a generalized Wakimoto module. So what is the difference? Let's think about classical situation. So there are Verma modules and there are Wakimoto modules. Both high weight. They both live in this category. But when it's not generic, they are not isomorphic. So, and the difference is that Verma module is generated by highest weight. So it's like a form, you have a highest vector here, and it generates the full module. So the n minus subalgebra is free over n minus. So n plus x trivially, n minus x free. Verma does not have this structure. So n minus is not free. So it's sort of, it's like opposite situation to Verma. If you know what contragradient Verma is, it's sort of in this direction. It's small, but it's sort of along these lines. one can be obtained from the other by sort of infinite listings. So perhaps SL2 picture would help. So SL2 Verma model looks like begin here with an action, free action of F element. So this is a free action, and E acts the way it acts depending on the highest weight lambda. So imagine that here I have 0, lambda equals 0. It means that here I have 0 action of E, and everything else is injective. The F's and E's from this part is injective. The Verma model, corresponding model, has a structure that this fellow is the model. So M minus 2 is a model of 0. Right, and the question is one-dimensional. This is structure. But now imagine that I write once and say that this is 0, but it's not. This is sort of a contragradient one, so I interchange. So this is no longer Verma because F is not injected. Okay, this would be a contragradient Verma, and it has same length, but now the one-dimensional model is a submodel. So now C is a submodel of, I will call it like that, M bar 0, and M bar 0 by C is M minus 2. So I interchange the position of two irreducible factors, right? One-dimensional and M minus 2. So before one was a submodel, now it becomes a quotient. Well, in the affine setting, you can do it in the infinitely many direction. That's why it's sort of infinite listing. Okay, then again, the wild idea was that it will not be a generalized Verma model for n greater than 1, but it will be a Wyacheslav model. So we don't expect, say, that the Lie model of the Lie component generates the full model. But nevertheless, the Wyacheslav models have a nice properties. The property that the character, the Wyacheslav model, is the same as the Verma. So the dimensions of the spaces, like in this example for SL2, the dimensions are all 1. And the models are different, right? But the character stays the same. And this turns out to be correct. Right, so the character will look like that. So this is the model we induce from, the tensor model, and then we're inducing for SLN hat, so we just act by a negative part, like here. And this will be our character. Okay, let me see. Yeah, maybe vertex algebras I leave for tomorrow. Okay, so this answered the first question that we asked. What would be the character like that? So you do restriction on SL plus 1. And it is not a generalized model, but it's a generalized model. It's not irreducible. Nevertheless, the character no. And it's done. Second question is
So thank you very much. Are there any questions for the speaker? Yes.
It was about one of your previous slides. So you can go back a little bit. I don't know.
More?
I'm afraid I'm not going to be able to answer the question.
I was going to ask something that occurred to me while you were giving explicitly the generators of these affine algebras. Has it ever been tried to put in them some sort of orthogonal structure, an inner product, to make it some sort of Hilbert space, which is invariant under the Lie algebra bracket? Is there something along that line? Would that help for?
Yeah, so in other words, could you maybe get integrate these representations even to representations of the corresponding groups?
Of course, behind Kac-Moody algebra, there are Kac-Moody groups.
Yeah.
Right.
If you assume that those X are diagonal,
Almost the same as having, that's the basis for, standard, finding standard basis for plot space, so that's almost equivalent.
Any more questions? If there are no more questions, then let's thank the speaker again. Now there will be coffee for, let me see, 33 minutes.